Hello everyone, my name is León and I'm going to talk about our work titled SuperPoint Features in Endoscopy. This work was done inside the context of the EndoMapper project, where our goal is summarized as real-time mapping from endoscopic video. We use computer vision techniques to create 3D reconstructions of the gastrointestinal tract. Here, we show some of the videos that were taken as secondary recordings, so the process were not modified for it. The problem we focus on in this work is feature extraction for matching in this real medical data. The goal is to find a good feature extraction model that works well in endoscopy images. This problem is really hard because of frequent occlusions, blur, liquids, and specular reflections that hinder visibility. The main contributions of the paper are both the proposed model for this task and the evaluation benchmark we created to validate this and other models. We'll start with the model, which is based on the deep learning framework called SuperPoint. SuperPoint uses a convolutional neural network with a typical encoder-decoder architecture, but instead of one decoder, it has two. The first one is the interest point locations, and the second one is for the descriptors of said interest points. A very important aspect of SuperPoint is that it is completely self-supervised. It uses different views of the same image, and since we know they represent the same scene, we train it to make the output of the network consistent. This way, we obtain a feature extraction network that doesn't need supervision at all, which is great for us because we don't have supervision for correspondences in endoscopy images. But then we want to go a step further and also tell the network that not all features are desirable, and those found within or near specular reflections are bad for 3D reconstruction algorithms. We modified the framework to add a new loss term. The right part is the output of the SuperPoint network, and the left part, the function M, is a mask that penalizes features on specularities. This function M is first a binary threshold of the image to detect the specularities, a dilation of the result to also capture the neighboring region, and a Gaussian blur to smooth the edges of this mask. The result is a loss that penalizes this kind of undesirable features. We want to validate this model against other well-known methods, so we propose an evaluation benchmark to do that. The model first was trained on a private training set of 11 colonoscopies, with around 100,000 images for training and 7,000 for validation. And the evaluation benchmark here contains videos from two different public datasets, EndoMapper and HyperVasir. EndoMapper also has camera calibration information, while HyperVasir does not. To generate ground truth for the validation, we used CallMap. CallMap is a structure for motion tool that computes camera poses from the frames of a video. In our case, the endoscopy frames give the endoscope poses. With that information, we proceeded to perform the experiments. In these experiments, we extracted features and matched image pairs 1 second apart from each other, with various well-known methods in this application. Matching in this environment is a challenging problem. Methods sometimes succeed, but usually struggle. In the first experiment, we measured the number of features extracted by each method per frame. We also counted the number of inlier matches that each method was able to obtain, according to Rassam estimation of essential or fundamental matrix or CallMap's essential matrix. And we also looked at the percentage of the image that contained these inlier matches to also control for the coverage of the methods. In these metrics, our model performed better than the others, especially in the EndoMapper's test set. The Hypervisor test set is very different from the one used to train the network. The model performs well, but the improvement is not as significant. And we also chose a second experiment where we used the method's features to estimate the rotation of the camera. We use ransack and estimate the essential matrix and compare it against Colmap's matrix. We show the error in degrees of the estimated rotation. We ordered the errors and here show the value. As we show, our method is much accurate when it comes to predicting the rotation of the camera, which is fantastic since our goal is creating 3D reconstructions. As conclusions, we proposed a feature extraction model adapted to endoscopy images. We designed an evaluation benchmark for other models to be compared against it, and released both of them to the community to use. Additionally, our model performs better in this domain than other well-known methods. Thank you very much and check out our paper for more details.